Now we will be examining serially connected resistors. Can we find the equivalent resistor to those which are connected in serial? So in this circuit we've got 7 resistors, 1, 2, 3, 4, 5, 6, 7. They are all connected in serial. Why they are connected in serial? Consider that R1 and R2. So two terminals of one of the terminal of each resistor is connected to a node. This is that node, and there is no any other resistor or any other element connected to that node. Therefore, R1 and R2 in serial. When they are in serial, the current of these elements, they are equal. Let's prove it. We need to choose the reference, current reference for this one. Let's say this is a I1, that is I2, that is I3, I4, I5, I6, and I7. So if you write the Kirchhoff current law equation for this node, it's going to be this current I1 current is coming towards the node, that's why minus I1, and that current is coming out of the node, so plus I2 is equal to 0. That means I1 is equal to I2. Similarly, if you consider this node, I2 is going to be equal to I3, so it goes like that, I3, and goes up to I7 equal. Let's assume that these all equal currents shown by I, so and show this as I here. Now that is a general rule that we can say that serially connected resistors currents are equal to each other. This is not only for the resistors. For any element, if they are serially connected, their currents are equal to each other. So this second step, our aim is to find what would be the resistor value which is replaced with these 7 resistors. This current does not change. So we are saying we are going to remove all that, put just one resistor. It is called R equivalent resistor value. Then this current doesn't change. So remove that, put this one. So same current. For the voltages, I didn't say anything because you're going to connect this independent voltage source here. We know that independent voltage source does not change wherever it is connected. So therefore Vs stays as it is, and we are saying this I and this I, if we prove that this I and this I equal to each other, then I am going to say this 7 element replaced with these equivalent resistors. The currents do not change, therefore this resistance value is the equivalent resistance value for these 7 resistors. So in order to prove that, we've got to write the Kirchhoff voltage law equation as well. This is Kirchhoff current law equation, and right now Kirchhoff voltage law equation. In order to write this equation, we've got to choose a loop direction. So according to passive sign convention, the current reference for this independent voltage source is going to be downwards. So if you write the first voltage, the sign is going to be negative because the opposite direction of this one and this one. So it's going to be minus Vs plus V1, V2, goes like that until Vr. All of them signs are positive because all these current references direction and the loop direction is the same direction. Therefore, they are all plus, equal to 0. So if I move that Vs to this right hand side, and I'm going to use the definition relation this time. Definition relation. So V1 is going to be R1 the current of this element, we said this current I1 is the same as I, so I put I here, R2, and the current of this element I2 is also equal to I put I again. So if we go that way, similarly, R7 time I equal Vs. So I move this one to here, so that has been moved here. That's why it is plus. Now if I put the I parentheses, these R1, R2, point R7 in I parentheses equal to Vs. So let's compare those two now. In here we've got I, this current I here. And in here, this format, if you replace all these addition of the resistance values as the equivalent resistors resistance value, then this is a definition relation of a resistor, isn't it? So this is like this. So this resistor's current is this in this circuit, and in this circuit we assume that that current is equal to this current is this, isn't it? So we found that this current and this current does not change. Therefore, if you replace these 7 resistors with that resistor, that current stays as it is. Therefore, they are equivalent. So we have found the equivalent resistors resistance value. The next step is, what's the use of that? First of all, if you consider 2 elements connected in serial, if you replace those 2 elements with an equivalent resistor, then one of this node will disappear. That means you are not going to write Kirchhoff current law equation for this node. If you remember, in the analysis we use the Kirchhoff current law equations, ND minus one of them, and then Kirchhoff voltage law equations, NE minus ND plus one of them, and the NE definition relations, totally 2 NE equations. So we are saying now, if there are 2 resistors connected in serial, this number is going to be reduced by 1. So if there are some other serially connected resistors within the circuit, for each serially connected resistor pair, you're going to reduce the number of equations here by 1. So that means the total number of equations that you're going to solve will be reduced. Therefore, it helps to analysis. So this equivalent concept usage for resistor helps to do analysis in a better way. So that is one of the advantage. The other advantage is all the resistance values are not available in the market. Let's say 56 ohm resistor is available in the market, and the 2 ohm resistor is also available in the market, and 58 ohm resistor is not available in the market. So not available in the market, then I can get that value, resistance value, resistor, by connecting those 2 available resistors in serial. Now this equivalent of this is one element with the resistance value 58. So I introduce this unavailable resistance value resistor by using those 2 market available resistors by connecting in serial. So that is another advantage. So in some cases we could use these advantages, so that equivalent concept is important. But you've got to remember one thing in here, that is I just missed that. That is, I can tell you. So this is quite interesting. We have many resistors, and we are replacing these resistors with one resistor. So element type do not change. Equivalent circuit element is a resistor, and before that equivalency, the elements, they were resistors as well. Why I am saying it especially in here, because we are going to see some equivalent circuits which are not like that. So there could be some other different type of equivalences as well. Just remind you that. So close that.